Hello, welcome everybody. Good morning, good afternoon, or good evening, depending on of your location. I am Vincent Soumois. I am the president of Fluid & Co. And I am happy to welcome you to join this webinar, Complete One-Stop Shop Solution for Plant Design and Simulation, in collaboration with the ESApro and PAS Suite teams. Let's start with the agenda. After a small introduction to present Fluid & Co., I will let my colleague from ESAin and ESApro P&ID present you their various tools, including a live demo on classical application that will jump from one tool to another. It will start with Leonid, then you will have Francesco, Sergey, Alex, and finally Francesco again. We will leave time for a Q&A session. May I remind you that you can ask your question during the webinar through the Q&A box that you are available. After that, a few words will conclude the session. Fluid & Co. It's a Canadian-based company based in Montreal for software representation and associated services in the following domain: pump with specs, optimization and SPM with Mode Frontier, digital twin and wind engineering linked to the BIM world with BOS and Vento, and also reservoir simulation with Echelon and GeoEO2. And we have also FIDESIS for the FEA simulation. But also we have the PAS Suite, START-PROF HYDROSYSTEM, FM Nozzle and Equip, and the ESApro Suite, but I will let my colleague describe them today in more details. A few slides about a customer. Of course, ESApro and PAS will also have 1,000 of users worldwide. They will show it later today. So I will give the end to Leonid, that will start with the presentation of the PAS Suite.
And thank you, first of all, for the opportunity to participate in this webinar. So you will see in this webinar the live PAS software demonstration, and I just would like to give you some small review of what is PAS software. So PAS software is a family of software which consists of several programs which interact with each other and which also interact with different computer design systems, and it covers main aspect of piping and equipment analysis. So there is a fluid flow analysis, it's PAS HYDROSYSTEM, and which provide hydraulic and heat exchange analysis and piping sizing. Then there is another software for piping stress analysis, including fatigue, stability, static and dynamic analysis. This is software PAS START-PROF. We also have equipment stress analysis, PAS Equip, and we also have PAS Nozzle Fam analysis for nozzle cell junction stress and flexibility analysis. So all this software was developed for decades with all experience of users, and we continue to develop it very intensively. Oops. Okay. What is the industries? So first of all, of course, it's process plant and piping, utilities, equipment for all kinds of process industries, refining, petrochemical, chemical, and biochemical and others, food. Another interesting segment is district heating, transfer piping and equipment. oil and gas gathering, distributing, storage, including offshore and onshore. And of course, all kinds of pressure vessels, including heat exchangers, tanks, and so on. But on this webinar, we will concentrate on two piping applications. It's PAS HYDROSYSTEM and PAS START-PROF for fluid flow analysis and for piping stress analysis. And we'll also show some opportunities of Nozzle Fam analysis in interaction and as part of START-PROF. So, besides very powerful opportunities for calculation, our focus is always on integration between all kinds of software, between parts of our software and CAD tools. And today we will also show you the integration with ESApro software. And of course, another feature is that it's very easy to use. It's have very good user interface, and it's very simple and efficient to use. So you will see it yourself. Regarding our geography, it's worldwide, and our users are in practically all big industrial countries. Here is the scheme of integration. So you see that our piping stress analysis software integrates with different our own software, PAS HYDROSYSTEM, PAS Nozzle Fam. It's a two-way integration. We can import, export geometry. We can calculate and get unbalanced forces from HYDROSYSTEM to PAS START-PROF. We can import geometry in from different CAD systems, and we can export drawings. And for example, we have different integration. We can export support data for LCAD and so on. It's a very big diagram. And a similar diagram for HYDROSYSTEM. Again, we have two-way integration through PCF file and NERTER file, and some special integrations with our own software and other CAD software. So what we are going to show you today in our part of webinar, after we will have 3D model in ESApro piping, we will have a PCF file exported from ESApro piping, and then we will import it to our software. We will show you basic features of our software, and also we'll show you how different parts of our system interact with each other. Forwarding geometry, forwarding results, forwarding unbalanced forces, and provide a solution for such cases as static analysis, for search analysis, and for two-phase flow, slug flow analysis. That's all what I would like to show you and talk, and then thank you, we said.
So thanks, Leonis, for this presentation. We will now listen to Francesco that will present all the ESA part of the software.
Good morning to all. I'm Francesco Pais from ESAin. I'm one of the member of ESAin developer team, and I'm one of the company founders. In this presentation, we will take a look to our plan design solution. Who we are. ESAin is an Italian company founded in 1994, and we are the first Italian provider for professional software for industrial plan design. We provide solution based on AutoCAD and BricsCAD. So is an AutoCAD application. ESApro is an AutoCAD and BricsCAD application. Currently, we have more than 800 customers and 4,000 licenses in Italy and worldwide. But in Italy, we are the main provider of plan design solutions. So we have more than half of the overall plan design seats here in Italy. And our solution is addressed to any kind of project, from big project in oil and gas industry, but also for medium and small project in other industries. So we have a wide range of application. Experience and expertise combined with direct contact, because we are the manufacturer of the software. So if the customer needs to any kind of question or problem, he can interact with us. We have currently 11 products. They are divided in 3 areas: the process design solutions, plant design solution, electrical design solutions. During this presentation, we will take a look to process and plant, and at the end, there will be another session for the electrical solutions. And here you have all the service we provide. The advantage is the easy to use approach. It's very, very user friendly. Not only the way of modeling a plant, but also the administrating part. Because if some of you are familiar with other tools, they know that the administration could be hard to manage. And the software is very proficient, so it reduces the times and costs, low learning curve. But most of all, you have the 100% pure DWG files. So you work with AutoCAD and BricsCAD, and you provide the standard files that can be opened with any other tool. And we have maximum flexibility with license management as well. Here you have the complete workflow between our application and the rest of the world. And here you have the project database, and this database is fed by the process part. So we will see how to create a process scheme that feeds the database. And we have another module for data sheet. We have an integration with electrical part. We have another tool specific for piping estimation materials. And here you have ESApro 3D piping, that is the 3D modeler for plants. And here you have the compatibility with the other tools for the other disciplines, the mechanical CAD like Inventor, SolidWorks, or whatever. The BIM compatibility with Revit or any other tool, structural, steel structure, or also laser scanners technologies. If you need to create a revamping, you can use a laser scanner. And here you have some additional modules. One is for the head loss calculation, another is for constructive support. And this tool is very important because this tool, stress interface, lets you to be compatible with stress analysis software, in particular with PAS. And we show you how to create a P&ID to draw a piping and export a PCF for START. Isometric sketches and cable trays. With the cable trays module, you can model electrical raceways, and with the cable routing module, you can route the cables inside the cable trays. You will see this at the end of this webinar. And here we have integration with other tools, PDM, PLM, Navisworks, viewers, and other competitor systems like Hexagon SmartPlant and PDMS Aviva. Here, an example of our customers, some of them. Most of them are Italian companies, but some of them are international group like Eni, the biggest oil and gas provider here in Italy. This is the first product, P&ID. So with this application, ESApro P&ID, you can create easily a process scheme. Here you have standard AutoCAD, and here you have the commands of the application. So you can start from a vexel, for example, and you can assign a name to this vessel, maybe tank 001, uppercase. Okay, and here you can specify the material, manufacturer, and so on. If you use usually storage equipment LTD, you can copy and paste the data, and you can generate a table just to show the equipment characteristics. Okay, here and there. And now let's start to draw the process line. The ESApro approach is a spec-driven approach. This means that when you draw a process line, you have to specify the size and the spec. This is the line number and the spec. This means that when you draw a process line, this line is connected to an equipment and has some properties. And when you will add a valve over a line, you will be guided to select the right one. Okay, in this case, I'm continuing this line. This is the line 6177. Okay, I connect this, and then I can draw another line, this one, and so on and so on. These are standard AutoCAD lines. ESApro doesn't use custom objects, so you are using standard AutoCAD entities. Okay, and this is the refill line. Okay, I have a flow conflict, so I can change the flow, and I tag this, this, and this, and I add a reducer. Okay, and double click to change the size from 2 inches to 1 inch. Okay, then you will see the spec-driven approach. When you select a valve, the software is asking you what valve you want to, where do you want to place this valve, and the software will suggest you the right one. Okay, in this case, only the gates and the swing check are compatible with this size. Okay, and I can add this and this. Okay, and if you don't want to this valve anymore, you can substitute a ball gate with a ball valve. And as you can see, this is a threaded valve, and this is a flanged valve. This is the spec-driven approach. So when you place a valve, the software will check if this valve is compatible with the line. In this case, is compatible. In this case, is not. And if you change the line size, this valve will be automatically updated. Okay. The valves are numbered automatically by the software. Okay. And you can look for a specific item, and you can save your data and get the lists. You can generate a line list, a valves list with the number of valves, the quantities, and all the characteristics. And here you can also generate a list with the tags, for example, the name and the ubication, or the legend. In this case, I'm generating AutoCAD tables, but you may also generate this list as Excel file. And now you can add the instrument part. So if you want to add an instrument over this vessel, you can pick a size for the trim line. Okay. And this is the number, the loop number, and this is the function. This is a LIT, and I paste this from my catalog. This is a Pyrex Saco Viscoral 50, and here you have the IO signal. This will be useful if you want to generate the IO list and continue to generate the loop. This is a level controller, LC. This is the function. And an electric signal from here to there, and the control valve. You may choose the actuator type you want to add, maybe this one. Pneumatic controls with spring return, and generate the balloon. And what is this? This is the level valve number 7. And with paste data, you can select, oh, I don't have this. Why? Oh, I made a wrong selection. It's not LT, but it's a level valve. And now it's compatible. Okay, the software checks for the instrument type. And here you have the electrical signal that from here goes to there, and it's terminate. No, my P&ID is terminate. And here you can generate an instrument list in Excel. And you can get an instrument list that consists of a list of many drawings. No, you can have many drawings. Okay. Once done, you can go to the piping. Close this file. Okay. I have this dialog. Okay, it's still open. Okay, close it and close this file. And here you have the 3D piping module. With this module, you can draw the pipeline in 3D. And here you have a window, a dialog that shows you if something is missing. In this case, the vessel is missing, the pump is okay, and so I have to draw my vessel and draw my pipelines. So I can take a reference point, 800. Okay, and I draw a vessel and I type the size. Okay, what is this? In this case, I can pick the equipment directly from the P&ID and associate the object. In this case, if you open the P&ID, you will see that this becomes red. Red means, okay, this object is made. Okay, if you have a mismatch, you get a red icon that shows you that this object is not aligned with the P&ID. So I can draw a nozzle now. Okay. I can assign a nozzle name and one. Okay, and then you can draw some steels, conceptual. Okay, I have some AutoCAD lines, and here I can draw a beam, for example. Okay, a line here and there, and this line, okay, could be here, here. And I can cut this with this coming here. And I can get these steels in my bill of materials. So I can get how many steels I have, or I can import my steelworks directly from Tikla or other tools. Okay, now you can draw the line directly, picking the same line number I had in P&ID, the line number 9700. Okay, pick here, and you can specify the length, or with the connect option, you can pick this point. And with the auto route function, I get the clash detection in real time. It's good. I can add a valve. The spec-driven approach gives me only the compatible valve. In this case, I can rotate this valve of a specific angle, 45, for example, and I can specify the distance from here to the nozzle, 1000. And now I want to connect this line to my P&ID. And in this case, is this one. Okay, so this line is complete now, is green. Okay, I made the same thing I made in P&ID, so I have to connect my outlet. That was good. Okay, with this specific icons, I can I have a tool that let me to guide my routing. In this case, I can specify the length, or I can touch this plane to get a track, a path. This is the manual routing. It's very useful because in this case you can control the route of your pipeline easily without having to calculate any dimension. Okay, this is the nozzle, and add the flange. Okay, and it's over. Then I can add a support here. I can add a U-bolt, for example. Or just this physical bolt. Pick this point, the length. Okay, and I can pick here, and this will be a constraint. Pipe support 100, and I will export this into pass. And this constraint will be recognized by pass correctly. I launch the data extraction to get the materials list. Okay. In Excel, I want to have the components. You may have a unique list for all the materials, or you can split them per line. For example, if you insert a column and set the line number, you get an Excel file and where the material will be splitted in line. And in this case, if you want to know only the materials that are located on line 9700, you have it. Okay, and here you have, okay, on layout, in layout environment, you can create your views, a plan view 150 from top. Okay, this one. Just forgive an idea, though. I'm going very, very fast, I know, but it's just to give you an overview on the software. I want to create a section view, one or two planes in this case. I pick one point, this one, another point, section view, and this is the model view. Okay, 3D view. Good. This is my layout is complete, and with this command here, I can generate 2D drawings starting from the model, and we get a flat view of my model made by lines, optical lines. I can add dimensions, overall dimensions, or I can add the tags. What is this? And what is this? Or I can tag also the line numbers, line tags, just to have a reference, between the P&ID and the piping. I have this line number. Last one, I will generate the isometrics. So I will go here. I launch the automatic groups generation. With this function, ESApro scans the whole model to see how many sheets I need to generate to perform the isometric sketches. In this case, okay, this could be a sheet, and this could be a sheet, but you may combine your line as you want. You can merge two sheets in one sheet, or you can split one single complex sheet in many sheets. You have the full control of this process. And with this command here, you can export your lines into ESApro Isometrics. In this case, okay, 3 lines. This one, take a look at this one. You will see this line in PAS. Alex will show you. Okay. The software now is writing the ISO file. The ISO file format is something like the PCF file format, is the our proprietary format. Okay. And this format is read by our software, ESApro Isometrics. So you can launch this to generate the isometric sketches. I'm left the mouse and the software is working by alone. And this is the final result. You have the isometrics out of scale. On the upper right corner, you will see the 3D line as it is in 3D model. Okay. And it's an in-scale representation, but the isometric sketch outside is an out of scale. Okay, you have all the nodes. Okay. This is the line. I will open this file again just to show you the final result with the balloons. And on the right side, you get the materials list, the weld list, the cut list, and any kind of list. Okay, close this and open this file, for example. Okay, this is the 3D line, and this is the isometric sketch. This is the piping support 100. And these balloons are for the materials. Material 1 is the pipe. Material 2 is the pipe as well, but different size. And here you have the prefabrication, and here you have the erection materials with the weight, the total weight, prefabrication and erection weight, and the total surface. And here you have the 2 supports, PS7 and PS100. PS7, I think, is something, okay, is here. Here you have all the welds, and here you have the weld type, butt weld, socket weld, or whatever. And here you have the cut list, as many pipes as letters. And if you have an erection weld, in this case, I want to mark this as erection weld. This pipe will be we have an additional length, E, that usually is 100 millimeters. You will calculate this again. 1 millimeter more. And you have the final here. Okay, this is isometrics. And if you want to export this into PAS Suite, you have to go on Extra menu, on ESApro Stress Analysis interface. You have to select the software you want to export to. In this case, is not written well. I have to fix it. And here you can specify the file name. In this case, could be 91. Okay, 9. Oh, this one. Save and select yes. Overwrite. Select this. And the software will generate the PCF. Okay. My part is terminated 25 minutes. I went a bit fast, but
it's perfect. Thanks a lot, Francesco. Let's start now with the simulation, and Alex will continue for that.
Okay. I don't want to share my screen anymore. Okay. Ready. Alex?
Okay, thank you.
It's your turn.
I hope you see my screen now. So this is the file that I received from Francesca. So how to import it? I just drag and drop this file into the past START-PROF, pipe stress analysis software. This file is opened. The code, we have a lot of different type of codes, pipe stress analysis codes. I will select the most popular. It is the B313. And now I need to add some improvements to this model. So first, what I will do is just select the wall thickness. I will just select the shadow 80, and select the material. After that, I will copy the properties from this pipe to the following piping. This one, this line. Okay. So now I will change the wall thickness of this pipe. I will select the schedule 80. Okay. And I need to select the material. After that, I copy the properties of this pipe to this line. I select which properties to copy. Okay. So now I will add the anchors, which will simulate the equipment. And our model is almost ready. I will just select here the sliding support. Here we can select the guide support, for example, like this. So now our model is ready. I will save the changes. Okay. So analysis is done, and we can check the results. For example, we can see the pipe stresses in different modes. We have main mode and test mode. Of course, we can check the support loads. We can see the deformations of this piping system. So let me show you the improved model. I have improved model with beam elements like this. I added this beam system here. It is just the beam element, the same like the pipe element, but this is beam element. We can select the section properties from the database. And also we have the internal support here between the pipe and the beam. The pipe can slide along its axis because we have the U-bolt here. So this is the guide support. Let me open its properties. It has the vertical restraint and restraint in X direction and the friction factors between the beam element and the pipe element. And we have two rigid elements here. Okay, so we have the valve and some equipment. So now I can save this model and pass it to the Sergey Lysin to analyze the water hammer effect in this piping system. Okay.
Okay, thank you, Alex. Hi, everyone. Thanks again for joining us today. Allow me to say a couple of words about our another software called HYDROSYSTEM. HYDROSYSTEM is a software where you calculate not the pipeline, but the fluid inside this pipeline. This is what we call a fluid flow analysis software. This is where you calculate your pressure drops inside piping systems, temperature drops, velocities, fluid flow rates, flow rate distribution, etc., etc., etc. And HYDROSYSTEM is having very strong, not only strong calculation capabilities, but also different interfaces with different software. First of all, just like in START-PROF in HYDROSYSTEM, we can import the same PCF file. So I can import the same PCF files from ESApro. But if you want to take more advantages and have a full cooperation between a HYDROSYSTEM and START-PROF software, we recommend you to import the START-PROF files. Allow me to import the file that Alex saved previously. So, okay. As you can see, it's the same model as we imported from PCF just a few seconds ago. But if you import it from START-PROF, you will get more features about concerning interchange of different data between HYDROSYSTEM, where you calculate your fluid flow properties and fluid flow analysis, and START-PROF, when you can calculate stress analysis. Because there are some processes where very important to take into account different forces, loads, and other effects that may cause the piping movement, etc., etc. I will go to this in a few seconds. HYDROSYSTEM is very easy to use software. Here you work with a piping system. You can input it on your own from different piping components, or you can import it from another software, as we did a few seconds ago. But we need to add some additional data. First of all, let's change the flow direction. Our flow will come from node 15 to node number 1. And let's say that our fluid in this piping system will be water, for example. Our flow rate will be, I don't know, 80,000 kilograms per hour, for example, and our inlet pressure over here will be about 2 megapascals, something like this. So after you set up this additional data, you're ready to go. You're ready to perform analysis. In HYDROSYSTEM, we have several types of analysis. First of all, we can calculate isothermal flow. This is where save the file. This is where we can calculate pressure drops, velocities, and other parameters, assuming that the temperature of our flow is constant. So the temperature is not changing. And as you can see, we can see what exactly is happening with pressure and other fluid flow parameters at each and every piping components inside our piping system. Or we can calculate heat and hydraulic analysis. This is when you calculate both, not only pressure drops, but also temperature drops, and you can calculate how much heat will be lost from this piping system and how the temperature would change in this piping system. And also in HYDROSYSTEM, we're capable of calculating transient processes such as surge analysis, or as we call it, a water hammer analysis. So let's calculate what will happen if we will close this valve. So when the valve is open, the pipeline, the fluid in this pipeline behave like this. And now we will do the following. We will close this valve, for example, quite fast within 1 second. So 1 second and the valve is going to be closed. And we want to find out what will happen before this valve over here, for example. I'm adding a viewpoint in here, number 1. And what will happen after this valve? Somewhere over here. Okay, and let's set up the calculation settings. For example, let's calculate what will happen within 5 seconds after our valve is start to closing. That's it. We're ready to go, ready to perform water hammer analysis. First of all, I will start with isothermal flow analysis to understand once again how piping system works when this valve is open. And now I will perform water hammer analysis. It will take about a couple of seconds. Come on, let's go. And it's done. Okay, now let's look what is happening before and after this valve. The more convenient way of doing so is to output the pressure charts for our piping point number 1 and node point number 2. And this is what is happening in these 2 points. As you can see, is absolute pressure in megapascals. So when we're closing our valve, we have a pressure rise. Not a big one, but It could damage your piping system if it's too big. So in HYDROSYSTEM, you can easily calculate what will happen if you open some valves, close some valves, when you start up the pumps, when you trip pumps, etc., etc. But that's not the only problem that may occur at water hammer analysis. Another problem is that this water hammer may cause loads on different nodes of your piping system. And to understand what will happen with your piping system at water hammer, you're not enough of having only HYDROSYSTEM. You need to use two programs, HYDROSYSTEM and START-PROF, because START-PROF is capable of performing this type of analysis. But to make this work much more easier, we can calculate and we can generate the forces, loads at all the nodes of this piping system in a special file for START-PROF. So to do this, I need to select Force Export, Water Hammer, not this, but to START-PROF, and generate spatial file CTPF extension, which consists all the necessary data for take into account this water hammer loads at START-PROF at piping stress analysis. So this is why we recommend to import exactly the START-PROF files, because if you import PCF files and in START-PROF in HYDROSYSTEM, we can have a different type of nodes, different nodes numbers. So you won't be able to export this data then to START-PROF if it wasn't imported from START-PROF. So to make this cooperation between these two programs works, you need to import START-PROF files. And after that, you give this file to your piping stress analysis team. So I once again give floor back to Alex Matveyev. Alex, show us please how to then use this file in START-PROF.
Okay, so now I need to import the loads from the past HYDROSYSTEM software. I open this model. And I receive the following file from the Sergey from HYDROSYSTEM. This is CTPF extension. Let me show you the properties of this file. It is very simple. For example, we have the node number 5. This is node number. And here we have just 6 forces, 3 moments, and 3 forces in X, Y, and Z direction. And the same with number 4, the node number 4, node number 3, and so on. All this data was calculated using past HYDROSYSTEM software, and each data is calculated at different time moments. For example, this is time 0.01 second. If we will scroll downwards, you may find a different time moment. This is a different time moments, and so on. So past HYDROSYSTEM automatically find the most dangerous, the greatest loads caused by the water hammer and export them into past START-PROF. So how to import them? I just open the operation mode editor, select Add Loads from File, and select this CTPF file. And START-PROF automatically create 14 load cases, additional load cases, with different type of loads caused by water hammer. So we can check that loads in START-PROF software. For example, I may open the node properties, open its properties, and we can see all the loads on this node, on this specific node from the water hammer. You can see the values of the loads at different moments of time. Okay, and the same with all other nodes. For example, this node, also you may open the properties and see the values of the loads. And now we can just run the analysis and check the results. For example, I will open the animation deformations of this piping system. This is a static analysis caused by the pressure load and thermal expansions. So we can see how does it work, and our beam model also is flexible, so it is moving. We can switch to another mode. For example, this is the test mode, test pressure, test weight, and the water hammer loads. But the most interesting is this time moment. So I will select it. And this is the movements of our piping system caused by the water hammer. So the greatest displacements, greatest loads are in this time moment. And we can check the stresses at each time moment. For example, I choose output, the pipe stress. This is the maximum stress from primary loads. It is weight and pressure. And from secondary loads, it is the expansion stresses caused by the thermal expansions. And you can select the specific mode. For example, this is the main mode, static mode from pressure and temperature. And this is the mode from pressure, weight loads, and additionally added the loads caused by the water hammer effect. And this is the test load in test state. And this is the maximum values. Also, we have a different representation. You can see all the modes and see the values of the stresses here at from different load cases. This is the main mode, and different modes at different from water hammer at different moments of time. Okay, so now we can add also the equipment. For example, here, let me check this picture. Here we have the pump, and here we have it's this line. This is what's happening. This is the line, and here we have the vessel, and this is the pump. So let me add the pump here. I will delete this anchor and add the pump element. We have different elements: air coolers, fired heaters, compressors, turbines, different type of pumps, tank nozzle, vessel nozzle. It is the smart objects. Each object can model the equipment in much details and check the loads, check stresses, and so on. So here I will use the pump object. I will just select some material and select some properties. I will not use two nodes. It will be just pump in one node. It will be top nozzle. I will just select the this. This is the axis of the pump shaft. So now I will add the vessel. Here I will delete the anchor and add the smart object vessel nozzle. For example, our vessel is 2 meters, it has the height of 2 meters, and we can specify the flexibility of this nozzle. It can be rigid. You can manually enter the information about this, the flexibilities of this nozzle. You can also enter the flexibilities using WRC code, but you have to specify its properties here, or PD 5500, or you can use the finite element method to calculate the flexibilities of this nozzle. I will show you the finite element method. And now you also can specify the allowable loads manually. For example, manufacturer of this equipment give you allowable loads. You can enter it here, or you can check the stresses using WRC code or you can check stresses using finite element method, or you can check the allowable loads using the finite element method. How to do this? It's quite simple. Just click here and pass Nozzle Fam software opens. This is integration, direct integration between START-PROF and pass Nozzle Fam, the finite element software, to analyze different type of nozzles and equipment. So here you select the base element. It can be a cylindrical shell, storage tank, T, different type of conical shells, different type of elliptical or spherical heads, including the flat heads. It can be rectangular plate or the band, for example, for trunnion elements. So I will select the vertical vessel element. The diameter will be 2,000 millimeters, wall thickness and other properties. I will just leave the default values because I just demonstrated how does it work. I will enter the diameter of the nozzle, the wall thickness of the nozzle, and some other properties. It can be radial nozzle or inclined, all that. For example, this geometry can be analyzed by WRC RC code, but it can be analyzed by the finite element method. But I will just choose the simple radial nozzle and click return to START-PROF. Oh, sorry. I did a mistake. Let me specify the height of this vessel. It will be 4,000 meters, like this, and this nozzle will be 150. Okay, and I click yes. So now the finite element analysis is working. This is the matrix. It used the shell elements to model the vessel with the nozzle and calculate the flexibilities and calculate the allowable loads of this nozzle. So now we can consider the local flexibility of the nozzle, but also I can add the global flexibility of the vessel. How to do this? I will just use the rigid element like this. For example, it will be the length will be 1 meter, like this. Weight is 0. And here I will put the cylindrical shell element, the special object, cylindrical shell. It will be, the projections are 0, will be minus 2 meter. Diameter is 2,000 millimeters. I don't remember the wall thickness. I will just use this value. And also you should specify all other properties. I will just leave the default values. It's just for demonstration. Put here the anchor, for example, but of course we can model, for example, the legs of this vessel. It is also possible. And now we can save our model. Let me add some name. Okay, so now we can run analysis of this model. I can recalculate all the objects, but I will not recalculate the finite element because I already recalculated them. And now we can check the results. For example, this nozzle, I open nozzle and equipment loads, and you see here the pump element, and you see the loads. This is the first nozzle. We don't have the second nozzle of the pump, so it is blank. But here we see the loads that is acting on this pump and the allowable load. This is the maximum values, so we can also check it in different load cases. And also we can see the loads on the vessel nozzle. It is the load that is acting on the nozzle, and this is the allowable load. And of course, you can check it in static analysis, from water hammer, in test mode, and so on. So in any operation mode, in any load case. Okay. So also, of course, you can check the deformed shape of this piping system. This is the static load. This is the load from water hammer. This is the static load. You can see the thermal expansions of this pressure vessel, for example. And of course, the finite element model allows you to calculate the stress intensification factors of all bands, key elements, and other. You can just enable the finite element calculation. In this case, for example, you can calculate the stress intensification factors of this band element using the finite element method. You just click calculate, and Nozzle Fam automatically calculate the stress intensification factors for this elbow. If I will enable this auto calculation for all objects, for all T's, bands, trunnions, and other elements, and if I will run analysis, Nozzle Fam will recalculate all the finite element piping components and calculate stress intensification factors, flexibilities, everything, allowable loads, everything that is needed to perform the pipe stress analysis. And after that, START-PROF will perform the stress analysis. Okay. Also, if you need more details, I had the training course on Udemy, so you can subscribe it and watch. There are about 25 hours of video with explanation, detailed explanation of everything. Okay, thank you.
And now the last part. The last part is for specifically designed for the electrical designers, and not only them, because sometimes also the mechanical designers have the needs to create the electrical raceways. Now, this tool is ESApro cable trays, and we are looking at a real model where the 3D piping is just an external reference. And I created the electrical raceways here, and here you have the layout with the 2D drawing generated from the piping. And now I will add a new cable trace here. This is the electrical cabinet, and I can close this. Okay. I put a symbol here. Okay. Another symbol for the routing is quite a bit similar to the 3D piping. So you can use the same tools you had in 3D piping to route the cable trays. And here you can specify 200 millimeters, and you can go up at about 25 millimeters. And another sign could be here. Where is here? Good. And then I can route my cable trays using these objects. So cable trays, cable tray line. I select the product. We have a catalog of commercial manufacturers that can be implemented by yourself. If you have a local manufacturer, you can add your local manufacturer easily. And you can start from this point, and then you go up to a plane, to this plane. Okay, I hide this. Is better. Hide object. Okay, it's better. Cable trace. Pipe them. Start from here. Go up to this plane. Okay. Then I want to go on this plane. Enter. And I want to connect it here to this plane again. And with the automatic dressing function, I can draw my cable trace. I can select the section orientation. The opening side, in this case, is up, and the cable trays are drawn automatically by the software. Okay. And here you can add your reducing T or the branch. Once done, you can update your drawings. Where I can close this. Yeah. Let me move this, my dialog. Open my window. Oh, it's good. I have a panel here that is hard to move. I want to, okay. Is it possible to move this? Anyway, let's try to automatic dress the line. Your screen sharing, stop the share, close this. Oh, just a moment, please. I can move this dialog. May I move this? Okay. I can hide this. Or annotate, pause share, or mute stop video. I'm trying to remove my palette because otherwise I can't use the interface. Hide, name, annotation, right hand. I have it. Okay. Let's close and reopen. Let's try again. With this one, I have the window on the same position, so it's difficult to set. Okay, can I? Is it? How can I move this palette, please? Disable annotation, hide video panel. No, show video panel, hide floating meeting control. Okay. Oh, I made it. Okay, that's good. Now I can launch this, draw profiles, monochrome, no external references, and I generate this. So this is the new the new drawing, and here I can launch the bill of materials, and here you can generate an Excel file with a list. Okay. Once done, where is? Oh. Okay, excuse me. I had a problem with my connection. Can you hear me?
Yeah.
Excuse me. I tried to close the palette, but I wasn't sure that I was showing my screen. Okay, I can continue my presentation. That's good. Now this is the drawing, and now if I go on the model, I can route my cables. So I can hide this, hide objects. Okay, I can go on wireframe, and if I go here, I can select to route the cables. So I have an automatic routing or a manual routing. To route a cable properly, I have to define where are the users, and this is a general cabinet, and here you have another user and secondary cabinet, A1, okay, and this is the pump cabinet, okay, and here you have the pump number 1 and number 2. Pump 1 and pump 2. Good. Once done, you can route your cables, but before doing this, you have to create the sections. The sections are the piece of cable trays where you have a unique route without any exit. Highlight section, okay, this, okay, and I can extract section and equipment, and I can route my cables, automatic routing, and here you can specify the cables you want to route, and here you have the first path, the second path, the third path, and so on, and so on. Once done, you can go here. Okay, I have the same problems. Each time I try to remove this palette, but I can't. Project list, let's go here. And okay, now the sections. Where is possible to hide this? I don't know. This palette is very annoying. and at the end, I will get an Excel file with all the routed cables together. But I can, okay, I can move it. I get it. Project list here. And I can get the cable routings and list of cables. These are the routed cables with a length, calculated length. Here you can route. You have a list of cables that are grouped by routing, by type. And this is 60 meters of cable, 22 meters of this cable, and then you have cables for section, and here you have all the routed cables with all the sections that are crossed by these cables, and so on and so on. At the end, you have the progress statistics that let you to know how many cables you have. 14, and how many cables are routed. When you go here, you can add a label that shows you the section name, section number 2, and the section size, and you have the possibility to show also how many cables are crossing this particular section. You have this cable here and this cable here and this cable here. Okay, it's handed. Excuse me for for the problems, but you know, in live demonstration it happens sometimes that you may have some problems with the interface in this case.
And now we want to show you quickly how to analyze the piping system for the slug flow. So we have the following piping system with some anchors, some sliding supports. It is anchor. The system looks like this. And I will pass this file to this Sergey Lysin. He will analyze this system in PAS HYDROSYSTEM software. Okay.
Okay, thank you, Alex. Let's go back to PAS HYDROSYSTEM. The water hammer is not the only one harmful thing that can happen to your piping system. We also have problems when we have two-phase flow, gas-liquid flow inside piping systems, because two-phase flow may cause different types of flow regime inside the piping system. And one of these flow regimes, or flow patterns as they call it in the literature, could be very harmful. I'm talking about slack flow, or you can call it as intermittent flow, or different types of name. Slack flow is when you have a severance between gas and liquid flow inside piping system, inside your pipe. And these liquid slacks, especially when they're moving quite fast, they can hit the different parts of your piping system. They can hit elbows, they can hit valves, they can hit T's, etc., etc. And once again, make quite a high loads on these valves, on bands, elbows, etc. And in HYDROSYSTEM, we're not only capable of calculating this type of flow, we're not only capable of calculating gas-liquid flow, we can also calculate, once again, these forces loads on piping components. And to demonstrate this feature, I once again will import START-PROF files. The START-PROF file, the file Alex just showed you a few seconds ago. Here it comes like this. Okay. So now we have this type of piping system. First of all, allow me to choose appropriate calculation methods. We have a special TUFFP methods for designed especially for calculation different types of two-phase gas-liquid flow, especially they capable of calculating slack flow parameters. And let's, for example, this time our fluid will come from here to here. And our fluids, this time not only fluids, we will have two fluids inside the pipe. The first will be water, and I'm gonna add another fluid. And let's say that our second fluid will be air, a pure air. So we will have a water plus air mixture in this piping system. And let's say that our initial pressure over here is about 3 megapascals. Our flow rate will be about 2,000 tons per hour. And our gas content, gas to liquid ratio, let's say it will be 10%, something like this. And we're going to close this guy over here. Going to add here some closed valve. So there will be no flow in here. Okay. Oh, sorry. 0. 1. So, okay. So that's it. We're ready to perform analysis. The same type of analysis as we saw before. There's a thermal flow, heat and hydraulic analysis. I will choose an isothermal flow. We have some zero length piping, but that's okay. That won't cause our calculation. And the calculation is done. First of all, we can find out what is happening, how the fluid behaves itself in this piping system. Our pressure drops, our velocities, our pressure, etc., etc., etc. And also we can view what type of flow regime or flow pattern we have at each piping component. And this is the case when we have almost on every piping component the intermittent, the slack flow that may cause vibrations, they may cause high loads on our piping system. So let's now figure out how to find out whether it's harmful for our piping system or not. We have a special calculation results tab called slack flow results, where we can see our liquid slacks parameters. We can see their frequency. It's a very important parameters because the slack have a special frequency, and the piping system itself may vibrate. We have a natural vibration, or how they call it. And if these frequencies are close to each other, we may face some resonance effects or something like this, which is not good, which will cause a very strong, very powerful vibration. So the piping designer should take this into account and to to adjust the natural frequencies of the piping systems in such way that they will differ from each other in about 20 or 40% or something like this. So this is very useful parameter number one. Very useful for parameters number two is slack parameters. Slack size, amount of liquid inside the slack, and velocity of the slacks. Why do we need these parameters? We need them because knowing these parameters, we can calculate the forces loads at all these elbows and other piping components where our slacks will hit. And once again, in HYDROSYSTEM, we have such capability. It can not only calculate these loads, but export them, not here, but over here, once again, to START-PROF. So I simply press this button. Once again, I will generate the CTPF file, the same it was for water hammer analysis. And then, once again, I give floor back to Alex, and Alex is going to show you now how to use this file in START-PROF and how to find out whether this slacks will be harmful or not for our piping system. Alex?
Okay, so here I have this file that I received from Sergey. So here the structure of this file is the same as the water hammer file. It is different values of the forces acting on the nodes at different load cases. Okay, so I will just open this file. I select the first operational mode, click Add, Loads from File, and select this CTPF file. So START-PROF automatically import 32 load cases from HYDROSYSTEM software. And now we can just check the values. For example, I open this band properties and see the values of the forces. So here we see it's about 4 tons acting on this elbow. And for example, if we will check another elbow, you will see different force values here. So now we can just run analysis and see how our system is working with the slack flow loads. START-PROF performing the analysis for all load cases. The analysis is done. We have the problems with the stresses. We can see some cells are red, so we have the problem. The stress is greater than allowable. And now we can check the deformed shape of this piping system. This is the static analysis, and here is the first load case of slack flow. This is the second load case of the slack flow. Let me reduce the deformation. So our pipe will fall from this support because the slack flow acting on this elbow and it's moving. This is the load case number 2. It is moving in that direction. This is load case number 3. So definitely this piping system is not good enough for slack flow. We should modify it to increase its safety because this piping system should not fall from the support. This is the main problem. And for example, 32 load case or 31, this one, you can see the great deformations. How to avoid them? Our goal is just to place the supports correctly. For example, I can put here the line stop support along the pipe axis, for example, like this, some friction factor, like this. Okay, and we have the line stop here, and now let's run analysis again and see how our piping behavior with this support. Let's check. Okay, analysis is done. And now let's see the deformed shape. I run the animation, and now you see there is no significant deformations because this support holding our piping system. So the main goal, usually it is the main goal, is to place the supports correctly to hold the piping system from the water hammer loads or slug flow loads. Okay, and another important feature is the calculation of natural frequencies. So how to do this? You need to select this option, dynamic analysis, and run analysis again. We'll have to wait a little bit more time because START-PROF will calculate natural frequencies of this piping system. And after that, we can compare the results with the frequencies, what was calculated using the past hydro system. From the past hydro system, we receive the natural frequencies equal to 0.86 to 0.27 hertz. So let's see which frequencies our piping system have and compare with the past hydro system results. We will just need to wait a little bit more time, and the dynamic analysis will be finished. Okay, it is almost finished. And now, okay, so it's finished. Now let's open the natural frequencies of this piping system, and what can they see? They see that the frequencies is the frequencies are much lower when the frequencies of the slug flow. It means that, and some frequencies is almost equal to the slug flow. So this means that our piping system will have a resonance with the slug flow, and it will vibrate with great amplitudes. So we need to improve our piping system and add more supports. And of course, we can see the normal modes of our piping system. For example, here is the dynamic analysis. And here, this is the first frequency, first mode of vibration. Let me increase the deformations scale. Okay, this is the first mode of vibration. This is the second mode of vibration. So it's obvious that we have to add the guide support here, or maybe we should add the line stop support here to stop this form of vibration. And this is another form. Let's check, where is it? Okay, here, and so on. So our piping system is too flexible to withstand the slug flow. We need to increase all the natural frequencies in this piping system. Okay, so thank you for your attention.